Hi everyone, I'm Yang Ni from Tencent, and now we are thrilled to share our work towards general and efficient online tuning for Spark. This is a quick outline of what we are going to talk about. We first introduce the background of Spark tuning and our architecture design. Then we present technical methods behind the system. After that, we end this talk with experiments and conclusions. Apache Spark is a unified engine for large-scale data analytics, which executes data engineering, data science, and machine learning on single-node machines or clusters. A Spark application is controlled by up to 116 configuration parameters, which determine many aspects, including dynamic allocation, scheduling, shuffle behavior, etc. The performance of Spark jobs highly depends on the choice of Spark configuration parameters. For instance, an improper configuration may lead to over 100 times the execution time compared with a well-designed one. Therefore, it's crucial to choose proper configurations to achieve high performance. In this work, we focus on tuning the periodical Spark job, which occupy a large proportion of Spark jobs in production. It's difficult to manually tune the configuration parameters of a Spark task due to huge configuration space and complex interactions among parameters. In addition, manual tuning is usually time-consuming and labor-intensive, and thus is hard to scale to a large number of tasks. Recent studies propose to utilize auto-tuning techniques to optimize the Spark parameters. Lots of methods fall into the scope of offline tuning. Concretely, they collect training samples by running jobs with different configurations on a long production cluster, and then train a performance model to suggest new configurations for Spark job. Training such an accurate performance model involves lots of offline job executions, for example from 1,000 to 10,000. This process is very time-consuming and expensive. During our attempts to apply these methods in real-world tuning tasks, we realized three limitations. The first one is limited functionality. Lots of methods are designed to minimize the execution time, that is, finding the fastest configuration. However, the goal in many scenarios involves the execution cost, that is, the cheapest configuration. In addition, the tuning result should satisfy some application requirements. The second one is high overhead. As we mentioned previously, many tuning frameworks belong to the offline tuning paradigm. It brings high overhead and often incurs data security issues and cannot adapt to dynamic workload. The third one is inefficient search, which arises from two aspects. First, large search space, and then intrinsic dilemma of black box optimization. To address these issues simultaneously, we present a general online tuning framework named OnlineTune, which can efficiently find the near optimal configurations that minimize the objectives under different scenarios and satisfy application requirements. Next, we introduce the architecture of OnlineTune. To deal with limited functionality, we first introduce a generalized formulation about the tuning problem, which supports various goals and multiple performance constraints conveniently. To solve it, we develop a robust Bayesian optimization-based methods. Second, considering the high overhead issue, different from offline approaches, we propose an online tuning paradigm, which we tune parameters along with the in-production periodical executions of each Spark job, thus incurring low addition execution cost as in offline methods. Besides, we design a safe configuration exploration method when suggesting new configurations. To support the dynamic workload, we design a mixed kernel-based method. As for the inefficient search issue, We also developed 3 innovative techniques within Bayesian optimization to accelerate tuning process. This figure presents the workflow of OnlineTune, which contains 5 components. The OnlineTune controller is responsible for orchestrating the entire configuration tuning process, along with interactions with the data platform and the users. The multiple-purpose surrogate models are to learn complex relationship between configurations and objective metrics or performance constraints. The efficient, safe configuration generator is to suggest a promising configuration to evaluate for a tuning task. The meta-knowledge learner is capable of leveraging tuning history from previous tasks. The data repository is to store tuning-related data, including run history, workload metrics, etc. After user specifies the tuning objectives and constraints, then the iterative tuning workflow is activated. Before the execution of a periodical job starts, the data platform requests the OnlineTune controller to pass a new configuration for this run. After the job execution is finished, the data platform submits the execution results to the controller. When the tuning is stopped, the controller returns the best configuration found during tuning. Within this system design, OnlineTune enjoys several features: generality, user-friendliness, safety, and efficiency. Next, we introduce basic problem formulation. The tuning objective is to find the near optimal Spark configuration that minimizes the objective and satisfies performance requirements. We provide a general tuning formulation that supports both different objectives and inequality constraints. Formally, we use Tx to denote the runtime function for the tuning task using configuration x. Let Px be the price per unit of time for all computing resources used in configuration x. Due to the unknown hardware types, price function is not easy to obtain. Note that the price function is positively correlated with the amount of resource. In this way, we use the resource function Rx to replace price function Px. With this formulation, we can choose different objectives with different alpha, and this supports application constraints too. We utilize Bayesian optimization-based framework to solve the generalized tuning problem. Bayesian optimization is a global search method which has 2 components: surrogate model and acquisition function. Surrogate model is to model the relationship between configuration and objectives. Based on the prediction of a surrogate model, the acquisition function balances the exploration and the exploitation to suggest a new configuration. Bayesian optimization search for the promising configuration iteratively. We adopt a mixed kernel design in surrogate model to support dynamic workload. Besides, we utilize Latin hypercube sampling to initialize search and depend on EI values to stop and restart the tuning process. Next, we introduce the details about the configuration generation. To achieve efficient, safe, and configuration generation, here we develop 3 techniques. The first one is adaptive subspace generation. As aforementioned, the complete configuration space is huge, which greatly limits the efficiency of the configuration search. An intuitive idea is to use a smaller configuration subspace that includes the most influential parameters instead of the original huge space to balance the trade-off between convergence speed and convergence result. We propose a method to adjust the size of subspace based on the tuning intermediate results. To deal with constraints, we apply the EI with constraints as the acquisition function, different from traditional EIC takes the probability of satisfying the constraints into consideration. Further, to explicitly ensure the safety of job execution, we propose to build a safety set using upper bound prediction from surrogate model. Put it all together. The configuration generator first builds the safety region and then choose the next configuration by solving the EIC. Objective function is not fully black box. We have the partial function analytical form about the resource function. We propose a method to compute the approximate gradient when conducting Spark tuning. To integrate the benefits of both methods, we alternatively apply approximate gradient and Bayesian optimization to select the next configuration, so that the combined framework balance exploration and exploitation well with a convergence guarantee. In the following, we introduce the meta-learning module. Now, we describe the design of a meta-knowledge learner, which utilizes meta-learning techniques to accelerate the configuration search. To enable meta-learning, we need to learn the similarity between tasks. First, we extract the feature vector of a tuning task from Spark event log. Then, we measure the distance between tasks by calculating the number of discordant parents of predictions. Based on the task feature and the distance from previous tasks, we can train a regression model to predict the similarity between two tasks. Further, we can speed up the configuration search in two aspects: initial design and surrogate modeling. For example, we can start Spark tuning with well-performing configs from top K similar tasks instead of searching from scratch. Next, we present the experimental results. We have implemented the tuning framework as a cloud service and applied it to Tencent data platform. The empirical results on public benchmarks and large-scale production tasks demonstrate its generality and efficiency when tuning different objectives. Notably, compared with manual settings, our service can save 57% and 35% of memory and CPU cost on average over 25,000 of in-production Spark jobs within 20 iterations, respectively. We also demonstrate the gains and overheads of online tuning on these tasks in table. Based on the results in this table, our service needs no more than 4 extra executions to amortize the CPU usage overhead on average. To further investigate the generality, we conduct end-to-end experiments on 6 high-bench tasks with 5 existing baselines on a small cluster, under 2 objectives: runtime and execution cost. Our framework achieves the best and consistent speed-up and cost reduction result among all compared methods. The ablation studies also evaluated the effectiveness of subspace adaptation, safety exploration, approximate gradient descent, and meta-learning module, respectively. Finally, we will end this talk with a brief summary of our main contributions. We present a general and efficient online tuning framework for Spark, which can tune various objectives while satisfying application constraints. To solve the generalized problem, we designed a Bayesian optimization-based solution along with a safe configuration acquisition approach. To further accelerate the configuration search, we developed 3 innovative techniques within Bayesian optimization. The empirical results on real-world production tasks demonstrate its superior performance. In the future, we plan to extend this framework to support more data analytic systems. That's all. Thanks for listening.